Cross-curricular links between science and mathematics. Whether cross-curricular learning ought to be adjusted has been a subject of debate among educationists for the most recent century. Still, right up till today, it is changing with respect to the views of how subjects ought to be taught. Should cross-curricular learning be utilised as a form of teaching in school? This presentation will look at particular references to science and mathematics and also the links to ICT and how it can be utilised to aid further backing. Development of cross-curricular. Some of the first evidence was gathered in the Haddow Report of 1931 and the Plowden Report of 1967, with various council distributions in the 1970s which encouraged teachers to experiment with the curriculum and the way that they taught lessons. The statement in the Plowden Report that children's learning does not fit into flawless subject classifications is often used in backing cross-curricular subjects or themes. The 1960s, 70s and early 1980s saw a move towards arranging the educational modules in primary schools and cross-curricular subjects or ventures as stated by Carr in 2007. The Three Wise Men Report of 1992 proposed that children ought to be gathered by ability, with the instructor's part to be an educator for the child. It was expressed by the specialist that consolidating lessons keeping in mind the end goal to make cross-curricular learning brought about poorly planned lessons and superficial learning for children. Although discrete subject teaching was acknowledged in primary schools, a 10-year study by Boyle and Bragg between 1997 and 2007 demonstrated that subjects continued to be taught in a cross-curricular route, at least for some of the time throughout this period. The study found that from 2002, schools started to reintroduce cross-curricular instructing, frequently for the practical reason that empowered them to meet the desire in the National Educational Programme that all children are entitled to a coherent, broad and balanced curriculum. Taking after this, the national curriculum was implemented. It stated that there was no detailed rationale for such a large curriculum. Therefore, the government were convinced that subject content and knowledge should be defined in a lot more detail for infants. The National Curriculum 2014 recognised these issues, expressing there is no single method for instructing, and urged instructors to be experimental and to choose for themselves. Issues and considerations for using these curricular teaching approach will now be considered. Concerns have been raised by commentators of this methodology, such as Moodys and Reynolds in 2011, who stated that it lacks rigour and pupils may not develop essential subject-specific skills. Another view, by Jerniak 2007, Parkinson 2010, and Barnes 2011, believe that subjects lose their identity, whereas Alexander et al. From 1992 believes that learning is superficial and fragmentary. One of the difficulties when arranging cross-curricular work is having an acceptable justification for incorporating subjects in the topic. A second challenge when creating cross-curricular work identifies with time. Planning likewise takes longer, particularly when the point is new, since the assets may not be secured in the school. Assessment is a further challenge from the educator's viewpoint. Studies by both Venville et al. 2002 and Rennie et al. 2011 examine that trouble of evaluating children's learning when using a cross-curricular approach. Having considered some of the challenges of using a cross-curricular approach to enhance children's learning, I will now consider the benefits. Starting with Ofsted 2002, who noted that one of the features of effective primary schools is the capacity of educators to plan open doors for children to apply the learning and abilities adapted in one subject to different subjects. Cross-curricular work is viewed as a prosperous approach for teaching and learning, as Hayes 2010 suggests. Cross-curricular teaching and learning has strong links with the constructivist perspective of learning, as children work collectively and learn from their own direct experience. Kerry 2011, who is a solid supporter for cross-curricular work, argues children need to be urged to draw together experiences from diverse subjects. This thought that learning is interrelated is backed via Carr 2007. Well-planned cross-curricular work helps children comprehend their learning on the grounds that knowledge and skills learned in one subject are used to reinforce and support learning in other subjects, which is stated by Hayes in 2010. Kerry additionally contends that cross-curricular work helps children develop thinking skills, for example, problem-solving and reasoning, a perspective backed by Barnes in 2011 on the grounds that children don't just apply information and abilities adapted in one subject to an alternate, yet will likewise orchestrate data and thoughts from a scope of sources, which is stated by Claxton in 2002. Connecting maths and science. VC and Gellier in 2000 state that at the heart of science is mathematics. This leads on to how cross-curricular teaching can be used to support mathematical and scientific understanding by giving the opportunity for children to apply knowledge to a meaningful context. Children have the opportunity to link their learning to experiences. Science relies on the use of mathematics to prove quantitative evidence on which scientists make comparisons and draw conclusions. In exactly the same way, school science relies on children's mathematical understanding as a base upon which to develop their ability in primary science. Making science fascinating and relevant to children is one of the key features of effective science teaching and learning, as stated by Harlan in 2006. Boyle and Bragg from 2008 found that creating cross-curricular connections empowered the schools to add an expansive and adjusted educational program. Applying measuring and data handling skills. Beginning with Jarvis 2009, who suggests that cross-curricular approach has provided a creative way of lining subjects through a common theme to give pupils a meaningful, practical and holistic context to learning that is very motivating. Pupils are helped to see the relevance of science and skills in the wider context. However, he goes on to say that some subjects do not logically fit within the same theme. Nevertheless, with mathematics and science, this is not the case, as both subjects seem to intertwine into each other. Measure, for example, begins in the foundation stages, through measuring heights, hands and feet, and progresses to measuring distance, capacity, temperature and much more as children progress through the key stages. An example of a science lesson can be seen on the screen. Another example is when children are measuring friction. They will need to know how to measure distance and which equipment to select to measure how far objects travel on different surfaces. This would lead to children using the mathematical knowledge of metric units. This interdisciplinary approach is not furthering children's knowledge of mathematics, but in fact showing them the importance of it, whereas the science is being developed and furthered by using mathematics. Both science lessons are examples of child-led investigations, allowing the children to access the mathematical skills and make links at their own pace. A possible disadvantage of this is forwarded by Harlan, who states that children can formulate misconceptions by recording the wrong data. The list of topics that could be covered between science and mathematics are vast. Topics such as the natural world, including both leaves and butterflies, linked to symmetry and patterns in mathematics, healthy eating linked to pie charts of food groups, bar charts for calorie counting and daily intake. Using ICT to interpret data. Interactive whiteboards can enhance lessons by increasing the pace of lessons. ICT enables lesson time to be used effectively to interpret data. For example, using pie charts, tables and graphs to draw information quickly with accuracy. This is useful for interpreting complex numbers. An example of the accuracy of ICT can be used in science is cited by Kelly and Steed, that state that real-life scientists use ICT to gather and manipulate data, to control processes and to communicate ideas and research information. Sharp et al. 2000 lists attributes of ICT that contribute to teaching and learning, such as interactivity, originality, speed, provisionally automatic function, along with capacity and range. Teachers believe using ICT is a significant feature in improving teaching and learning, as stated by O'Sullivan et al. 2005. Even though ICT enables pupils to watch an experiment on the interactive whiteboard, they do not get a real hands-on feel for experiments. Hiscock 2012 states that if children are not given practical experience of measuring capacity, they have no understanding of what a millimetre or 1 litre represents. This presentation has considered cross-curricular issues within science and mathematics. It has perceived that there are difficulties for instructors when embracing a cross-curricular methodology and has concluded that there is no acceptable message concerning how to accomplish powerful cross-curricular learning. Choices about when and how to make connections between subjects will rely upon their instructive reasons for embracing this methodology. There is ample literature that states the benefits of cross-curricular teaching. However, there is not enough evidence to prove its effectiveness. Although the idea of teaching mathematics and science is as one subject seems beneficial, it still outweighs the lack of research done to prove its effectiveness.